Physiology Gone Wild. What goes wrong in shock? In our last lesson, we learned about normal cardiovascular physiology. In this lesson, we'll see what happens when things go awry. My name is Jim Lavelle, and I'm an associate professor of medicine at the University of Colorado School of Medicine. We're going to learn about 4 shock states here. We'll pick up where we left off with this busy slide that basically contains all you need to know about cardiovascular physiology. The cardiac output flows through the arteries, and the resistance in these arteries, also called afterload, generates a pressure difference across the vascular bed. The cardiac output depends on preload, or the venous return, according to the Frank-Starling relationship. Inotropy and contractility describe the relative strength of the heart muscle. We'll use this understanding of cardiovascular physiology to describe the shock states resulting in abnormalities in inotropy, preload, and afterload. Let's examine now what happens when contractility drops. Negative inotropy leads to a reduction in cardiac output. Applying Ohm's law, we see that unless afterload changes, blood pressures will fall. When reduced cardiac output resulting from a weak heart, negative inotropy, leads to end organ injury, this is called cardiogenic shock. Recall that cardiac output depends on preload, as described by the Starling curve. As preload decreases, so decreases cardiac output, taking us from here down to about here. When inadequate circulating blood volume leads to decreased preload, which thus reduces cardiac output, blood pressure is reduced according to Ohm's law. When this leads to end organ injury, this is called hypovolemic shock. Now let's look at afterload. When afterload falls inappropriately, the pressure generated from blood flowing through the vascular beds falls according to Ohm's law. When the drop in blood pressure that occurs with inappropriately low afterload results in end organ injury, this results in distributive shock. Let's recap. Having learned the concepts of contractility, preload, and afterload, we now have a framework to understand 3 of the 4 shock states. Reduced contractility results in cardiogenic shock. Reduced preload results in hypovolemic shock. And reduced afterload results in distributive shock. That wasn't too bad, was it? Unfortunately, there's another shock state that's going to require some mental gymnastics to apply this framework. Not to worry, because failing that, our next shock state passes the bloody obvious test. Hopefully it's not too great a stretch to grasp that a process that obstructs filling or emptying of the heart is going to cause some serious problems. Framing this in terms of our cardiovascular parameters is a bit more challenging. A process that prevents the heart from filling by obstructing blood flow into the heart functionally reduces the preload that the heart sees, and a heart that doesn't fill can't pump. Similarly, a process that prevents the heart from emptying by obstructing outflow from the heart dramatically increases the afterload that the heart sees, and a heart that can't empty doesn't generate much cardiac output no matter how contractile it is. When a process obstructs blood flow into or out of the heart, resulting in reduced cardiac output and blood pressure such that end organ damage occurs, we call this extracardiac obstructive shock. So there you have it, 3 key cardiovascular parameters and 4 types of shock. Understanding the pathophysiology between each type of shock will help guide diagnosis and management. Feel free to review this material as much as you need in order to feel comfortable. Until next time, we'll see you.